Okay, so stochastic. So I was saying, you know, your job is to, I don't know, check the design of the plane or something, you know, and you want to know you want to do a dynamic model of this structure, and you want to know what is the time history of the stress here during turbulence, right? Well, you're not going to be designing for a specific excitation on the wings for a particular turbulence, because, you know, the turbulence could be very different, well, not very different, but, you know, we don't have, it's not this kind of problem where the PT is not. So in a stochastic loading, we are satisfied with describing the loads in terms of certain statistical properties of the load. We can say, okay, the load has this kind of, you know, time, well, I'd have to have language from, you know, the Fourier domain, but basically we can say we know something about the loads, but we don't have the loads described in terms of precise time histories, right? I don't pretend to know that the pressure that the turbulence is going to put on this wind is exactly this curve, right? What I will have is a description in terms of some sort of a statistical nature. The same thing might be the case if I have a building and I'm trying to design it, let's say it's a very important case, maybe not a routine building, but I'm trying to design some structure for earthquake excitation. Well, every earthquake that we measured already happened, right? So the earthquake that the structure is going to be subjected to has not happened. Therefore, I do not have the time history of the true event. Now, I can, of course, generate some guesses or look at how the structure would have behaved to prior earthquakes and so on. Or I may simply say the earthquake itself is a stochastic process where the fault breaks, and then I have some vibrations that emanate and reach the structure. And so what I want to do is some mathematics that will allow me to generate different ground motions for which I can study the behavior of the structure. So in a deterministic case, we know what the load is as a function of time. In a stochastic loading, we describe the loading using well, I was going to say this using statistics. Let's just say that we don't describe the loading in a deterministic sense. We describe the loading in terms of some of its statistics. Okay. We can also have, in description of loads, loadings which are parametric, for example, right? Oh, no, something else with the stochastic. In the case of a stochastic loading, we might have a situation where the loading is stationary or non-stationary. Again, these are all idealizations. What we mean by the loading, the stochastic loading being stationary, is that if time is going like that, and we took a look at any time, what's happening here looks the same as if I look at another time, in a certain reasonable window, right? So the properties of the excitation, even though describing this statistically, are not varying with time, right? While a non-stationary excitation is one that would vary with time. Now, it's all a matter of scale. For example, if we look at an earthquake, you know, there's going to be something like this, and then this thing goes down. So there is a build-up, right? Where the load is growing, then there is a strong motion, and then there is a decay, right? Now, is this stationary or non-stationary? Well, that actually depends, because if I have a structure whose natural, let's say this was 3 minutes. And I have a structure whose fundamental period is, or whose reaction time is, let's say, 1 second, or something like that. Then, once the structure gets here, this lasts so long, given its own fundamental period, that the load feels stationary for the structure. So I may be able to do an analysis using stationarity in this part, even though the load as a whole is obviously non-stationary because it had to grow and then it had to come down. So the distinction between these two things is not like there is a sharp thing, oh, this is stationary, this is non-stationary. It depends on the structure that is being analyzed. The point is that if you are able to assume that the structure has had enough time to develop all its response so that it wouldn't really matter if the load lasted longer, we're not talking about fatigue, then the load can be treated as stationary. If the response is really if the duration of the loading is sort of small or is varying quickly with respect to the fundamental period of the structure, then the response may be necessarily non-stationary or transient. For example, it may be that, again, using the plane flying smooth air, right? And then here there is turbulent air, sort of in this boundary. And so the plane's coming like this really fast, right? As it penetrates this thing, that response is clearly non-stationary, right? You get this boom, 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 right? This thing. And usually it may be that if the turbulent air lasts a long time, by the time you get here, it's just kind of stationary because it's just doing the same thing. But this transition here from the smooth air to the turbulent air is clearly non-stationary, right? The response might be much larger than once it settles down. All right? So once again, and to conclude, this is a matter of, it's not like you can just look at it and say station. I mean, in idealized terms, yes, but in reality, it's a question of, can I treat the problem as if the duration was indefinite, or do I need to account for duration fundamentally because the problem is non-stationary? Okay? Finally, let's conclude with types of problems, and this finishes the discussion. We can say that we have the forward problem, and the forward problem in dynamics is the one that will concern or will take our attention for the large majority of the class. Okay, we'll do a little bit with something else, but in the forward problem, this is what we have. We have some structure, which I call omega. We have some excitation, which I call PT in general. And we're interested to know what's going on. Right, the output. We want to know the stresses, we want to know the displacements, we want to know something. So this is the forward problem, typical. We have a model. Actually, I should say we have a model. So we have a model of the structure, we have the loads, we want to know what's going on. There is also the identification problem. Right? In the identification problem, which we do in the class that I teach, I believe, next semester, or sometimes, basically what we say is, okay, we have some excitation, we have measured some output, and what we'd like to know is what is a good moment. So in the identification problem, we use the input and the output, and there are variations. Let's say in the simplest version, we have this input and the output, and we'd like to know something about what is the model. What is the model that is in the middle that makes this input, gives this output? That's the identification problem in its most simple form. We may have the load identification problem, in which case we have a model and we have an output measured, and what we'd like to know is what was the loading, right? That's the load identification problem. Now, I think I'm going to try to put in this class a little bit of this problem on the load identification part. And the reason why it came to my mind to do that, not only because I've done a little bit of research more or less recently on the topic and published some things on it, but because I was in Portugal in a conference this summer and ran into a PhD student that was finishing his work, and he had been reading some of the stuff we were doing and so on, and his problem was really interesting on this identification. His problem was that of, you know, an icebreaker. So you know these big, huge ships, right, that are used to break the ice in the, you know, in the very northern and southern latitudes, so that you can go through, right? So how in the world, I mean, you know, when you're going to design these ships, what is the force that the ice is applying to these ships, right, as it goes? How strong is this hull need to be when it's and so on? Now, of course, you can make, I'm no expert, I assume that they would have, you know, significant models, and depending on the thickness of the ice, of course, it's going to depend on all kinds of things, right? But what they're trying to do is to say, wouldn't it be nice if we could have, I don't know, you know, some sensors here. We cannot really measure these loads from the ice, right? How would you measure that? But let's say we were able to measure, I don't know, you know, the accelerations that are taking place at some points in the ship as it's moving forward, and that we somehow could use a model of the ship, right? We could use a model of the ship. We could use the measurements of not the measurements of the load, we don't know that, the measurements of something, like let's say this response, and that we could estimate somehow the ice related forces. Okay? So this is the input identification problem. So we have the forward problem, which is the typical one. We have the ID problem. We have the input ID problem. And then we have also the control problem. Now the control is actually a field in itself, so we're not going to really do control here, but I mean in the control problem the idea would be you have the system, you have some loads, right? You have some output, but you don't like the output. What you'd like is you want the output to be something you want. So you take the output, you put it in through something, which we'd call, let's say, the controller. Right? And the controller will do some calculations using this output, and then the controller is going to apply control forces. And then the output will be what we want. Or that we like, right? So we have the forward problem, which will take our attention in the class. We'll have the identification problem. We have the input identification problem. This one we will take care of. This one we will do a bit. This one is a course by itself. This one is several courses in various departments here, electrical and mechanical, although we're not and we're not, you know, dealing with it in this class at this point, although we will learn really the essentials of what is needed to be able to tackle this problem, or a lot of what is needed to be able to tackle this problem in this class. Okay, so with this, I think I'll give an end to this first lecture.